Okay. Okay, this is the example. The World Bank maintained the extension collection of the data about member nation. So health data, which you can download from our LMS system. So they examined the 38 countries, the population and all this different kind of the information. Okay, so one thing is what you can see is the female population and the male population. Actually this is the problem. This is in percentage. So female population is 70% means the male population is 30%, right? If the female population is 45, then which means male population means 55. This is exactly related because the male population will be just 100 minus female population. We cannot say this is the 100% perfectly correlated. This is the exactly multicollinearity linearity problem. That's why we cannot use both of them. We should drop the one of them when we do the regression analysis. I will jump into our R example. This is the PCA.R markdown file, so you can see. We will read through the CSV file, the health file, and head means it will show the first few rows. So actually this one has the death rate, health expand, life expectation, male mortality, female mortality population, female population. As you can see, this is a 51.07, which means it's a 48.93. So actually we don't need both of them. We know one and we can calculate the other one. Total population, labor force, fertility rate, birth rate, and so on. Now we will do the regression with our original data, which means is we will use total population, labor force, and so on. So first we're gonna do the scale. So this is the scale is the function that standardized our data. So I don't have to worry about anything. This one will just automatically scaled. Scaled is the we calculated the standard the mean and standard deviation, and then you calculated the z value, how far my number is from the mean value, using multiple of the standard deviation, just like a z value. Here I wanna predict. Okay, I wanna predict the life expectation using all other numbers. So the first column is the country name. So country name is just okay. Let me show you. This is our data. The first column is country name. So we cannot use these country names for our calculations, right? So I'm gonna drop to the name of the country name, and then life expectation will be the dependent variable. So I'm gonna take it out, this life expectation. And then I'm gonna take out this male population percentage because that is perfectly correlated to the female. Actually, you can calculate the male population once the female population is given. So we cannot use both of them. It will be a problem. I can show you why this can be a problem. If I don't drop this -9, okay, and if we run the regression here using this one, so here the minus means I will not take out first, and I will not take out fourth, and then all other columns. I didn't specify the row here, so I didn't specify row, which means I will take all the rows. Okay, and then I'm trying to find the life expectancy using all the data. That's why I didn't type anything and then just start, and then using this my data standardized. ST means it's standardized. So if you run the regression, what you can have is this one here. Male population is not available, now available, now available. Why we cannot have a male population not available? Because that is the perfect linear combination of the female population. So that's why. So I'm gonna take it out. Okay. And then I can learn it at the same thing. Actually, it will be exactly the same. But you can see the R square will be about 97.5% and just R square is a 96%. It's pretty good. However, the p-value, only the significant value is the health expenditure, right? So if I use only the health expenditure, what you can see here is the R square will be just 40%, right? If we include everything, your R square is like 97, but if you take only one, this is just 40%. Now, let's do the principal component analysis. Since we already do the standardization here, standardization by applying the scale, we will keep using. Pro-comp is the PCA function in R, so you can use a it should be the pro-comp. Principal component, so my data, and then you created a principal component, and you can see the principal component here. So what you can see is this one. I think this is. I think you can see here. That would be better. So first one is the summary. Is you can see what is the standard deviation. As you can see, the first one is the biggest variance, right? So that's why the standard deviation is the biggest, and then getting smaller and smaller, right? And the proportional variance is like 92% of it actually what it means is it captured about 93% of the total data variance. This one takes only the 2.9%. This one takes only 0.22%. So actually what you will expect is if you use only this one, actually it captured about 95% of the variance of the data point. So PC1 will be pretty popular. I mean the powerful here. And what is this numbers means? It's a PC1 as a life expectation times this. This is all the coefficient for the life expectation. So I should not use. Yeah, I should not use the life expectancy. That's why. Okay, so let me fix it. I should not take first column of my data. Okay, so this should be. Okay, now you can see here the meaning is still the same. Yeah, now this is the difference. PC1 takes about 2 standard deviation, and this is a decreasing, and this capture only 45% of the the total variance of the data, and this one has take a 23%, and this is a 16% and 7% and so on. Okay, so again, what is this number means is so PC1 death rate, this is the coefficient for this number. Of course this is we use the standardized number, so we are not directly putting in the death rate, but we are using standardized death rate into here, and then multiply this number plus standardized health expenditure times minus 0.30468670 plus and so on. Then you can calculate the PC1 for the first country, and you can calculate the PC2 for the second country, and so on. So this number, so 0.0454, okay. Okay, I don't know what was the first country, but if you take a look at it in my data, my data standardized. This is a standardized one, okay? So now I should be, this is the first countries, okay? So, can I see? So I can calculate here minus 0.25630677, which is this number, times this number, right? 0.15065,186 plus, and the health expenditure, this is a minus 0.414128 times this one minus 0.3046 dot 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 plus, right, and then third number is 0.0383 times this number, right, 0.4078, and then if you do the all of this, that will be this number. This will be the same as 0.0458413. So this is the principal one for the first country. I don't remember what was first country, but this is a country. Okay. So using our original independent variable, we created a new independent variable, but this one captured most variance of our data point. Okay. So in that way, we calculate. I don't have to calculate by myself. This automatically calculated all the PC1 value, PC2 value, PC3 value. So this is like a coordinate of the new axis, PC1 axis, PC2 axis, and so on.